While sine and cosine started their lives as trig identities in right-angled triangles, they are much more heavily used in modeling because of their periodicity, the repeating structure to the functions when they're used over positive and negative angles of any size, and also because of that up and down repeating shape that we see that mirrors some natural processes. Whenever we have a pattern that we see in some data that has that kind of cyclic behavior, then sine and cosine are natural choices to experiment with to try to capture that behavior in mathematical form. When we use trig functions as part of modeling, we generally need to translate them or scale them in various ways. For example, the graph y equals 10 plus 4 cos of x has an oscillating behavior, but the 10 and the 4 change it in ways that might make it more suitable for a particular application. Take a look at the 4 examples here and see if you can identify the graph based on what you know about shifts and scalings. If we have this 10 here, that is a shift up by 10, and this 4 is a vertical scaling by 4. What that does is expands the oscillation so they go up by 4 and down by 4. That's important to note, it's both directions. What we would see is an oscillation pattern that cycles around 10 instead of the usual 0. If we draw those y equals 10 lines on each of these graphs, we'll see these various options, and that rules out A pretty quickly because the center of the oscillations for A is somewhere around 4 or 6. The other ones look plausible though. What else do we know? Well, we know that the cosine graph usually starts high. It starts at 1 in the regular cos of x graph. So if we have plus 4 times cos of x, that means we are going to start at a height of 4 because of that vertical scaling. Well, we start at 4 and add 10 to it, we're going to be starting at 14. And so we're going to get the graph here of B and not C and not D. D doesn't go high enough, and A starts low and then goes up. That's not what the cosine graph does by default. When we're looking at trig graphs specifically, there's some common terminology that we use. We can talk about the vertical shifts and scalings, but we can also talk about amplitude of the oscillations, and that's how far up and down the graph goes around the center. And the average value is going to equal the shift that we had, because usually the cosine graph has an average of 0. So if we take the cosine graph and add 10 to it, then the average gets moved up to 10. This is the kind of terminology we would use with trig functions like sine and cosine, rather than the scaling and shifting, though they are equivalent. Moving on to horizontal translations and scalings, let's see what else we can do. If we have the cos graph, just regular cos of graph of x, the cos graph has a cycle length of 2 pi by default. It takes 2 pi radians to complete one full cycle of the cosine or the sine graph. If we put, for example, a 2 inside that function, let's make it a bit different. Let's make it 3. Remember what that will do. It will compress that graph horizontally. A bigger number means more compression, and what that means is we'll be able to fit 3 cycles of the cos graph into that same period that we had before. So being more explicit here, the period is 2 pi up here, whereas for this scenario, because we had a larger value here, things got compressed, so the period got smaller. How do we achieve that? Well, the period is taking 1/3 of what it used to take, or 1/3 times what it used to take. And in the general case, that number doesn't have to be larger than 1. If we have cos of an a times x, it'll have a period of the 2 pi divided by that a value. That deals with horizontal scalings. What about shifts? Now this is a bit trickier, and there's different terminology, so we're not going to get too caught up on words like phase. What we're going to be looking at is a graph like the cosine graph, and a term we can agree on is where it starts. So the cosine graph hits a peak at its start. Then if we introduce a shift horizontally, then what we're doing is moving where that start location happened. Now to answer this question, where does this actually happen, we're going to have to use a bit of reverse processing. And the idea is we know that cos of 0 is 1. And what we're interested in now is where does cos of ax plus b equal 1? Well, it equals that 1 at x equals our start value. Let's put that on the graph with that label. Well, let's take a look at those two equations. What do they have in common? They both have the 1 on the right-hand side, and they're going to have to then have the same interior, or up to 2 pi rotations. But it's easier to keep it as the same interior. And so it's going to happen when 0 is equal to ax plus b, or when x, bring the b over, we get negative b, and we divide through by a. That's going to give us the point at which the graph starts, or where it hits its first peak after the x equals 0 point. So this would be the graph of cos of ax plus b, going up to a peak of 1. So let's talk about that, looking at a function written out like so, and identify the various pieces. First of all, we have a vertical shift of 5. That's going to be the average. We're going to have taken the cosine graph and shifted it up by 5. Then we're going to have this 8 in front of the cosine. The cosine graph usually goes up and down by 1. Now it's going to go up and down by 8. That is what we mean by amplitude. Next, on the inside here, we have this pi multiplier. And so the period is going to be 2 pi divided by that multiplier here. And so we're going to get a period of exactly 2 units. It's going to take 2 units to complete 1 cycle. The last part is more interesting, and we put this form a little differently. We put constant times x minus something in brackets. And so what we're going to do is maybe not talk about the phase explicitly, but talk about the start of the cosine graph. When is that going to happen? It's going to happen when 0 is what we get for the whole inside, just like we did on the last page. Now with this new form, we can actually cancel out the pi, and we get x minus 1, or x equals 1. And so if we go to this formula here, if we plug in x equals 1, we're going to get a 0 inside the cos. The cos is going to be as big as it can ever get, and we're going to get the largest peak value on our graph. Now we'll go for the sketch. Let's make this 5, 10, and 15 here. We've calculated the average was going to be 5, so the oscillations are going to be around y equals 5. They're also plus 8, which will take us to 13. And they're down by 8, which will take us to negative 3 on this axis, on this scale. And we were told that at x equals 1, that's where the graph starts. We were also told that the period was 2. So we're going to get back to that same point after 2 units, and then after another 2 units. How do we fill in the rest? Well, at the adjacent points, we're going to be at the average. That's how we get a cos graph. We start at our peak and then we go down. And we know we're going to hit our minimum halfway in between, like so. And we can actually continue that back down to here. And with all those pieces in place, we can get quite a reasonable graph sketch happening for our function, like so. That would be the graph of y equals 5 for the vertical shift, 8 for the amplitude, cos of pi for the compression, and the x minus 1 in parentheses there leaves us with a peak at x equals 1, That's where cos has its value. Of, the interior value here becomes 0, and at cos equals 0, at cos of 0, we get a peak in the cosine graph. That last part tends to be the most confusing for folks. I would say the best advice is just not to overthink it. When does this whole thing equal 0? When it equals 0, cos is big. Okay, this equals 0 when x equals 1. That's when the cos graph is big.